So we can start. We were doing WGAN in the last class. So WGAN is a GAN that is derived from Wasserstein distance, and Wasserstein distance, sometimes it's also called earth mover distance, and it's a better distance compared to KL divergence because it is actually a metric. It satisfies triangle inequality, okay, and symmetry and so on. And there are many convergence proof as well, okay, which we have not seen. Now those convergence proof also tell you that it has many other interesting property. So if you are a real math student with some background in topology and something, then there are proofs on WGAN, especially the Wasserstein distance, is that it satisfies so-called weak topology, okay, and hence, but whereas KL divergence norm leads to strong topology, okay, and so these proofs I will see if I have to do. It's in the main WGAN paper. They have proved all these results, very concrete results. So what I will do today is that WGAN and more today, okay. So basically WGAN we have derived, and what are the things related to WGAN, mostly with implementation, but then I will end with some proof also. So that's the plan for today. So I will say it's WGAN and more, okay. So WGAN, what we have seen in the last class is that it is derived from the metric which is sometimes also called earth mover distance. So this is defined to be the infimum over all the joint probability distributions PR, PG, and you are trying to minimize the expectation XY coming from the joint X minus Y norm, okay. I will need one more class just to derive or to explain that this metric is a special case of a transport problem that people study in optimal transport. Optimal transport. So yeah, so here in optimal transport they study transport basically. So how much mass one can go from, how much effort one needs to go to take this probability distribution to this, okay. So this model that you see here comes from a transport problem, and transport problem is a lot more general, okay. So this is just one special case of the cost function or the metric that you are going to use, but you can change this metric and even you can get various types of earth mover distance, okay. And in fact even in those this is just W1 okay. So but then I could have P here, okay, then it becomes W Wasserstein's P metric, okay. So there will be one class devoted on optimal transport, and this will be seen as a special case of that, okay. And we will study optimal transport as a generic cost function, and then we will see how the community is kind of trying to find a tractable solution to this, okay. So then there are ideas like, okay, Sinkhorn algorithm and so on. So I will look into that. So original problem can be defined in a continuous framework, and then they go to linear programming as well. Again, control which is there. So what I'm trying to say is that there is a very generic framework here coming from optimal transport. So it deserves one class in itself. So we will do that very likely in the next class. Today we will remain around WGAN. So we knew that this is not tractable, and then we used Kantorovich Rubinstein duality. This was the main spotlight of the last class. We proved this theorem, and so as I said, what we are studying WGAN is a small subset of what people study in optimal transport. Hence, you may have this in your mind. This is Cedric Villani, film medalist, French guy, and the book is Optimal Transport. If you really want to refer more, old and new results. So that's a book. Okay, it's you can say that it's a main reference book in this community. So all these things, controversial duality and all this, you can see this in a very generic form there. And what Kantrovich gave us is that he told us that we can have this seen as a supremum over one ellipsis functions, okay, where h is one ellipsis, and then is x from p fx. So this is what we derived in the last class, and x follows p theta fx. So where the supremum is taken over all one ellipsis functions, right? So that's what we have seen. And and in the original WGAN paper, what they say is that having one ellipsis may be a lot more restrictive. So let us allow k ellipses. Okay, so let us replace 1 by k. Okay, so that's what we did. So they in the WGAN paper took it as k ellipses. Okay, and if you do that, then instead of wp p theta, you will get a k times wp p theta. So this implies k times. So it will be a constant scaling. Okay, and that should not matter, because as such, this is a supremum problem, and if it's constant there, then it should be achieved for the same p theta. Okay, so as such, there is no difficulty except for up to a constant that I may allow k ellipses as well type of functions. Then Kantrovich pulls you until here, and from here you think of writing a min-max problem that can generate. Okay, so until here it looks like some measure between p and p theta. Okay, so yeah, and even p theta is not known yet. Okay, but the idea here was, which I also wrote in the last class, is that here I will see this x being generated via some g theta z. Okay, so that's the change we do. So we want the samples x to be generated via some generator, which we call it, usually we call it push forward. Okay, so push forward is like usually you do push forward when you have something known and then you want to achieve something new. So in our case, this is x that we want to generate. So the trick that we do here is that replace x by g theta z. Okay, so and we learn g theta z by optimizing the z theta. Sorry. Okay, so that so overall it becomes a, and the f will start acting like a critic. Okay, it will say whether it's a good sample or not so good sample. Okay, so that's the key thing here. So if we do that, then so what we say is that we will choose, obviously this critic also will be parameterized. Yeah, the notation should be clear, I think. So sometimes I use h and okay. So what we can say is that we have W coming from some W, expectation of X, P, and I use some parameterization of F. Let us say this is HWX, where W is the parameter or the weights of, let's say, neural network, okay? And Z follows PZ, and this is HW and G theta Z, okay? And I'm supposed to minimize G over theta as well. So that's a min-max problem we have. Because it's an estimation problem here, so that's why we have to do this. So we have to find a theta for which the overall quantity is decreased, okay? So that's why we have a minimum here. If you don't do the minimum, then it means that kind of PR and P theta are kind of, you know that distribution, okay? You know that distribution and you're just computing the measure. But in our case, it's not like that. In our case, this is being estimated. So a further step is when I put some P theta and I want to overall minimize this error or distance for the theta, okay? Because I have an estimation going on here. So we have this minimization problem, hence it becomes a min-max problem in the end. If I don't do this, then it will say for a fixed P theta and PR, this is the estimation of the W distance for a given PR P theta, but I'm not really given, I have to compute this. So I put a generic P theta with variable theta. This is not variable, this is fixed, okay, let's say. So then it's will be overall, I want to minimize this. So then we can now write the algorithm. It's like it's a custom to write algorithm, okay? So otherwise sometimes I will be told that didn't write the method, okay? So although the method is quite clear, so this will take whole board, I guess. So algorithm for WGAN, I will write a little bit small, try to fit. So as usual, when we actually do computing, there are a lot of parameters involved, okay? So in this case as well, 0.00005 and C is 0.01 and M is 64 and N critic is 5. So what do we require in this algorithm is alpha, which is the learning rate which we have specified. So learning rate corresponds to the gradient descent, right? So that's the learning rate. C is the clipping parameter. So as you can see, these HWs, right, what we have, they are supposed to be K ellipses, right? So from the theory of GAN, it says that it must be like this. So now to employ this constraint, when doing gradient descent, you are working with gradients. So then you have to do the gradient clipping, okay? Because these guys, so if I take a gradient of this, so basically K continuous means the gradient of H is norm of the gradient of H, okay? I mean, this notation is a little bit misleading. So K continuous actually means this. Okay, say a function being K continuous means that the norm of the gradient is bounded by K. So hence in WGAN you are supposed to do gradient clipping. So when you are doing SGD for let us say max update, then you will do gradient ascent, and if you do gradient ascent, then the gradients that you are getting should be clipped by K. So here C is the clipping parameter, and that is taken to be 0.01. Okay, that's worked the best for them. Okay, sometimes there are parameters in the when you do the actual implementation, even from theory you don't know what is the best clipping. Okay, so in their case they choose this clipping which will clip the weights. Okay, so if I'm not wrong, okay, so let us see with the algorithm. So alpha is the clipping parameter. C is the clipping parameter. M is the batch size. Okay, and because this is supervised learning, so we will take a couple of samples. N critic is the number of iterations of critic, per generator. So if you remember in the original GAN also, we were doing k iterations of the discriminator. Here the critic refers to discriminator, okay? So in the WGAN they call discriminator as critic. Okay, so in the original GAN they did k iterations. Here also they are trying to do first n critic iteration, then do one generator iteration, then n critic, and so on. Okay. Okay. What other things we want is W naught, the initial critic parameter. Initial critic parameter for us, critic is HW, right? So the parameter is W here. Okay. So obviously W0 indicates the first, because it's an iterative method. So W0 will indicate your initial W that you are going to give, because you don't know, usually in an iterative method you don't know where to start, right? So you will start with some W naught. It could be random, it could be 0, depends, and then it will keep getting updated via gradient descent. Similarly, you have to run iterations for theta. Okay, so it's a max over W, mean over theta. So since it's a max over W, you will do gradient ascent and keep updating the W. Okay, so initial W is W naught. And similarly, we have theta 0, which is initial generator parameter. So I'm writing it small, trying to fit this in one board. Okay, now we start a while loop. So while theta has not converged, so theta is the generator loop. Okay, theta has not converged. So this convergence test could be done based on the norm of the gradient itself. Okay, if the norm of the generator, let's say with respect to theta, reaches certain value, then you can stop. So the convergence can be set by looking at the gradient norm. For t equals to and this may not necessarily have to be 0. Okay, that's the point. So it's the generator, what is the optimal value generator can take? Okay, what is the optimal value discriminator take? Because it's a min max problem, right? So not necessarily it has to go to minima explicit or maxima. Okay, it has to go to saddle point. Okay, so t equals to 0, n critic. So for each iteration of the generator, you are doing n critic, or in fact n critic plus 1 iterations of the critic, which is the generator here. Now we will sample now real images. So sample xi, I equal 1 to m, and they come from the real distribution. Okay, so this is a batch. So I have m number of images taken now, the real images. This is a batch from real data. Okay, so it could be image, it could be text, whatever you want to generate. Okay, it's very generic in that sense. Okay, it does not only work for images. Recently we did a publication on circuit data. Okay, we were trying to generate some electronic circuit data using this. Okay, so sample zi, I equal 1 to m. Now this is obviously samples from known distribution, and it could be, let's say, uniform. Okay, so uniform 0 1, let's say. Okay, so or Gaussian, standard or normal. So this is taken from pz. So in the algorithm it says a batch of prior. Okay, so by prior it means some of the known distributions that you have can be taken as a like random sample. Okay, so a batch of priors. So for your information, I can write this as uniform 0, 1 or standard normal 0, 1, because these are the distributions I know how to sample. Like the jets should be those which you definitely know how to sample. Okay, although they will be random. Okay, but that should be known distribution. Okay, so we take real images, we take, you can think of this as fake data, and this is the real data. Okay, okay, then we have a gradient computed for the critic. So critic goes with the weight W. Okay, so then let us say the gradient is denoted by GW for a short notation rather than using the nebula notation. So this is the gradient with respect to W. Now where are the W in here, right? So W I see here and here. So obviously I have to take gradient of these terms with W. So and it's an expectation, right? So it has to be calculated over the samples that I have taken. So this expectation value will be calculated for the samples being taken. So hence it will be sum of f of xi's. Okay, so fw or hw, I don't know why I keep changing. Sometimes I have fw, there I used hw. So let me use hw then, since we started with hw. So this is hw, and xi I equal 1 to m, and then I have 1 by m as well. Okay, and minus the other expectation, which is 1 by m, and sum of fw g theta zi. Okay, so this you can think of as sample average, a sample mean. So when we did statistical estimation, look, HW follows P distribution, right? HW follows P distribution, and Z is following some PZ distribution. So in the statistical estimation, what we said is that no matter what, we may not know the distribution, right? So let us say in this case I have sample x1, and then I did some experiment, I got sample x2, x3, but these guys come from some unknown distribution, right? This distribution itself I don't know, right? Because P here is some real distribution which I don't know. Okay, even if images I know, but I don't know which distribution. In fact, that's the goal of generative modeling, is to understand which distribution it's coming from. So you may say that how can I calculate expectation of some samples where I don't even know P? Then the idea here is from statistical estimation, which says that sample mean is an estimation of the true mean. Okay, and what we are seeing here is a sample mean. Okay, so this is our sample mean, right? So a sample mean was given like this. So this is, and sample mean also works for the function of the random variable. Okay, so all this is well defined. So hw x1 plus hw x2 plus dot 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 plus hw xm by m. So this is the sample mean. So we did a few more results on this, like if you do the sample mean for very, I mean, decent amount of sample, then it actually approximates the true mean. Okay, so that's what you have to do in practice, right? Because you can only work with samples. So these are sample means of hx, a random variable, sample mean of I mean hw random variable, and then the other random variable h of g of z. So h of g is a function applied on z. So that's another random variable, and essentially we have applied it's a kind of expectation of function of a random variable, and we have to compute the expectation. Then we took the statistical way of estimating that. Okay, so this, you can say that this is an approximation. Okay, approximation of the actual expectation that you had, but that's how we build algorithm. Okay, so we have to do some approximations. Now once I have the gradient, and this Inside I am optimizing the weights of the critic, which is our discriminator, and the gradient we have computed for the current W. Now we are supposed to update the value of the W, knowing the gradient with respect to W. So that's called the since with W we have a max, so it has to be gradient ascent except step. Okay, so this is W. New W will be old W. So I hope you don't get confused with this W here. So W is, you put old W plus alpha times, and let us say your favorite descent algorithm. So we know SGD, but then there are we know so descent algorithms, right? So we know SGD, and we know SGD with momentum. So there are like quite a few. Okay, I'm just listing in case you want to explore this. Okay, RMS prop. Usually I will do this in optimization course, but okay. Adam. Okay, there are many. Okay. Adagrad. So it's like, from optimization point of view, there are many possibilities one can choose, but from my own experience and what I have seen is that these guys are decent. Okay, you don't usually get anything exceptionally better than these four. Okay, either you use Adam or RMS prop. Adam is a extended variant of RMS prop in the sense that it does some bias correction as well. So there is an additional step here, but otherwise for practical purposes you can use any of these. This is an optimization topic, so I won't go there. So I will just say that use one of these which are known to be good. So this is RMS prop. Let us say in what they have done, WGW. So RMS prop algorithm needs your current W and GW, and inside that RMS prop also have its own parameter, which we are not showing it here. Okay, so there are hyperparameters here in RMS prop. Okay, so those that goes with momentum. So there are hyperparameters involved here. Okay. And this may be dependent on our problem, okay? Because RMS prop that the optimal hyperparameter is used to do some other minimization problem. So sometimes when you're writing code, you tweak these hyperparameters involved in the optimizer for your case also, okay? There is no universal tune. That's why they are called hyperparameter, okay? There is no fixed parameter. So there are parameters involved here, so the paper does not show explicitly, but those things you may see discussed in the numerical experiment part of the paper. Okay, but those things are not that important. That's usually experimental thing. Okay, so then we clip W itself. Okay, so the way the algorithm does is clips the W itself. Okay, so because some ellipsis continuity needs to be maintained, so it clips the W itself. Although I am wondering if we clip W within a range, it should kind of propagate to this being satisfied. Okay, which we may have to prove additionally, or it may have been a heuristic that seems to work for them. Okay, so the algorithm says that clip the W itself. So W clip the W in the range of minus CC. Okay, which is, it seems like W will be the entries of W, all the entries of W will be within the interval minus 0.01, 0.01. Okay, I hope I understand this. Okay, I have picked this from the papers. I hope I understand that this is exactly what clipping does. Okay, so you clip the weight W, and the idea here is that it should propagate to HW being K ellipsis. Not very clear right now. Maybe it needs a little bit more A little bit more work on that. Okay, so will this guarantee gradient being less than k, right? Less than k, or in this case maybe less than c. Okay, I don't know. Anyway, so this is the clipping of w itself, and then we end the for loop here. So this is the critic, the discriminator loop. Okay, it ran n critic times. We sampled real data, m of them. We sampled fake data from the known priors, m of them. We computed the gradient, and we used the sample mean to have the expectations, and then we have the gradient, and then we did a gradient ascent. So that's why this is a plus here, because it's a max problem. So this is ascent. Otherwise you will do the descent in the mean problem, and use RMS prop, which is a well-known optimization method, first order method. And then we do the gradient clipping, okay, where we restrict the weights between minus c and c. And now this was inside, and then now we go to the while loop, and we see what generator is supposed to do now. Okay, so this is our while loop, and so the generator usually plays with Z only. Okay, critic has like, yeah, so but here generator is only looking at Z, and it's producing some output based on that. Okay, so since theta is involved only in the second term, if we are to compute the change of this whole thing with respect to theta, that's what we want, then this has no theta, so it goes away, and then we are left with gradient of this term. Apply some chain rule and so on. Okay, so this is the process. So we will sample, because for the second term it's with Z, so we only need the random samples for the generator. Okay, because for computing expectation for the second term only Z is needed, and Z is the fake data. So we will only sample m fake data again. Okay, so sample Z I equal 1 to m, and these are coming from the prior distribution, a batch of prior, right. And then we do the usual gradient computation. So g theta, we put minus grad theta 1 over m sample mean. So this is fw g theta Z I equal 1 to m. Okay, and in the second line itself, this is the last line basically. So in theta we do the gradient descent. So theta minus alpha, again we are using the same RMS prop, and that takes theta g theta. Okay, and all this, and then this is and while. Until now, WGAN and its variant are the state of the art on GAN based model. Diffusion models are good, but they are suffering from slow sampling and so on. So still this is the most popular in many cases now. Diffusion models training is very costly. So of course that will get improved, but the quality is very good in there. So for all practical purposes, on a small scale you can think of, but then, and for many problems this has been developed in such a way that you can handle a lot of applications. Diffusion models have been restricted to very special class for the moment, mostly images and so on. GPT is not really diffusion model. GPT is based on transformer, okay, chat GPT. So that's based on pre-trained transformer, and we will look into that. So that's another way to, so you have to really get into the transformer model. Okay, so we will do that. But DALI 2 is based on diffusion model, okay. But for the moment, WGAN has been used in many places now, music generation, okay, and so on. So we don't know whether diffusion model will take over. We don't know. Diffusion model is very recent, like last 2 years or so. So, but for the moment, I would say WGAN is a lot more in practice still. So this is and this, as we have seen, this is a simple extension of the GAN. That's why it's called, still it's called GAN with a W as a prefix. And there are like practical aspects that you will know while you are coding yourself, okay. So there are many codes available. I will put some link of the course like Jupyter Notebook and so on. At least you will run it for yourself, okay. Ideally you try to implement this, okay, then you get the proper understanding. But there are Jupyter Notebooks not very big, 60 lines or something, you implement everything. From technical point of view, these things may look, the main heavy computation that you can think of is the optimizer itself, right? So this is the heavy computation, so-called heavy, right? Where you're computing the gradient, and why it's heavy is because these are neural networks, right? So these neural networks architectures themselves are very complicated, okay. So if I'm using some let's say architecture specific to this, right? So GAN, I mean CNN type architecture that involves convolutions and so on. Doing this gradient yourself, it's almost impossible. So you do this, you send this to PyTorch basically, okay. PyTorch modules to compute the gradients for you, okay. And so you just have to tell the functions and the point where you want to compute the gradient. The library knows these functions because you have defined these functions for the library, because it's a neural network, so there is layer-wise architecture. And the whole thing gradient, which is the only computation, to be frank, needed, is this main thing, because this is simple gradient descent only. So so this is done by library, okay. So this essentially is a one line in Python, okay. This is also one line in Python, okay. So I said 60 lines, which itself may just refer to how you are processing the data itself, okay. So you will be taking data from somewhere and so on, processing the data and then these things. But these essentially are one line thing in Python, okay. This is also one line in Python, okay. You do like PyTorch dots optimize or something like that, okay. You give this parameter and it does that for you. Clipping is obviously one line. Generation again is one line, and this gradient computation again will be one line, okay. Approximately, I'm saying, okay. So usually my students do this coding. I don't explicitly do myself, but Python is very high level, so it's simple to implement these things. So this is the WGAN architecture, and so experimentally what did WGAN guys found out, okay. So there are few proofs they have done, but they have also noticed few things. So the few points that GAN has a better performance, right? So WGAN compared to GAN. Okay, these are some observations. Empirical, you can see, okay, what they found while running, okay. So what they have found is that WGAN does not require maintaining a careful balance in training discriminator generator, okay. So I think there is a stoppage. Continue. Okay, so there is a backup actually. So bad luck. Okay, so what they said is that WGAN does not require maintaining a careful balance in training. So what many things you will see during training, I mean doing actual implementation. So when they have GAN, so when because these things, you know, these things are parameters here, okay. So sometimes theory and experimental, okay, requires some tuning there. So in this case, how many times you will update the discriminator weights, right? So this itself we have to play around basically, okay. So numerically, a few additional things we have to do. So what usually they found in the GAN is that this is very like sensitive. Okay, if you do too much, it starts failing. If you there are a few issues, right? Something called mode collapse and so on. Okay, I will go into those things maybe in the next class. Okay, what is the meaning of mode collapse? Basically, mode collapse means that GAN starts cheating in a way that GAN starts producing the images that it has learned well and just keeps producing that image. It does not create the diversity that you need. Okay, so that's in a very but we can explain that a bit later. Okay, so that's called mode collapse, where you are looking for a lot of images, but then because generator is always taking the Z, right? So it's like passing an exam where you just write the same answers repeatedly. Okay, and the discriminator doesn't know, because discriminator is looking at the questions that, okay, discriminator doesn't know how to look at the diversity of images. The discriminator is only looking at the current cat image that's coming. Is it corresponding to cat distribution or not? It's just that. But discriminator does not have of the knowledge of how to check the diversity. Okay, so next time again the generator produces the same image, discriminator say it's good, you are doing well. So if you're doing well, then don't do any update. So it's essentially generator is tricking the discriminator. Okay, so that's called mode collapse. Okay, and that's okay, so that's related to how the training goes. Okay, if you kind of overdo, or there is a concept of like overfitting here also. So if you do too much training of the discriminator, then also you will be having problems and so on. So here WGAN is not that sensitive. Okay, that's what they noticed in their experiments. So WGAN does not require maintaining a careful balance in training discriminator and generator. Okay, essentially how much will be the n critic and so on. Here it's not that sensitive. Okay, so usually it's more stable, and WGAN reduces mode dropping. Okay, dropping, or we can say reduces mode collapse. Okay, so that's an improvement over GAN, and these are the things usually it will be very hard to kind of prove. Like I have not seen explicitly someone proving this, but there are different proofs that the author has done. Okay, which I will try to prove, let's say. Okay, maybe in the next class then, but it will be very difficult, I would say, to relate directly from theory that it will prevent mode collapse and so on. Okay, so there are a few things observed numerically here. The disadvantages of WGAN is that it requires this weight clipping to somehow implicitly or somehow maintain these k-ellipses continuity. So this can be a disadvantage. So weight clipping can lead to so obviously there was improvement on WGAN itself. Okay, so that improvement I can also tell you. So improved training of GAN, that's the paper that came after that, and what they noticed is that this weight clipping that we do, W that we wrote here, was creating a bit of instability, and they improved it further, and they had one interesting result, and using that they added something called gradient penalty. So improvement of WGAN. Okay, so basically we are going right till the most latest thing that one should do with WGAN. Okay, so this is, I would say, the most stable variant, okay, with the gradient penalty. So this was introduced by, so introduce gradient penalty. It's also called GP. So hence the WGAN now, the most stable one that people use is they call it WGAN GP. And this was introduced in the paper Improved Training of versus time GAN. Isan Gulranjani et al. 2017. Okay, so this was, as such, this paper was very light, like there is nothing more. Just they add one penalty term in the min max term objective. They will just add one extra term, and they do it with just one observation there. Okay, but this improvement was quite taken very well, and so so what they do is, okay, so what I will do is that I will straight away go to their main result, and they their main focus in this improvement of WGAN is this gradient clipping, okay, which created instability while running WGAN. And to remove that instability, they had this one result here. So this one result, and then WGAN plus gradient penalty. That's my objective now. So, so in this paper, they had this proposition: let PR and PG be two distributions in X, a compact space. Okay, don't worry if you don't know compact space, compact metric space. Then there is a one ellipsis function f star, which is the optimal solution of the WGAN with the Control-Which formulation. So which is one ellipsis max, and then expectation of Fy, Ypr, and then minus expectation of Fx, xpg. So yeah, so there exists a one ellipsis function f star, which is the optimal solution of this. Okay, so and then let pi be the optimal coupling between PR and PG, defined as minimizer of WPR PG, which is the original form, right? So infimum of over PR PG, expectation of xy follows the joint norm x minus y, and where obviously pi PRPG is the set of joint distributions that we have seen in the last class. So that's the formula, original W distance, right? So where pi PRPG is the set of joint distributions, and pi xy is pi xy whose marginals are PR PG, then if f star is differentiable, and xt is tx plus 1 minus ty with 0 less than equal to t less than equal to 1, it holds that p x y, yeah, I mean they have written like that, but that's fine. Okay, so grad f star xt being equal to y minus xt by norm of y minus xt is equal to 1. Okay, I will explain what is going on here, but let me first finish this. So yeah, so this implies f star has gradient norm 1 almost everywhere. Okay, let us try to understand what this theorem says, and what could be a possible improvement in the WGAN. Okay, so what it says is that let PR PG be the distributions, two distributions in X, compact matrix space, and then there is a one ellipsis function, which is the optimal solution of this. I mean there exist. Okay, so it's not like we are assuming this. So let PR PG be the two distributions in X, and then there exist one ellipsis functions, okay, f star, which is the optimal solution of this. So that's fine, because we are looking for maximum over one ellipsis, okay, for this type of f, and then the existence is there. Okay, so there exists an f star for which this happens, but then what it says is that yeah, so then if f star is differentiable and xt is some interpolated point or convex combination of x and y, and what it claims is that gradient of f star xt, which is so probability of gradient of f star xt being equal to y minus xt divided by norm of y minus xt is 1. So and then the corollary follows from here, and it says that f star has gradient norm 1, because that's fine, right? Because this probability 1 means that this f star is equal to this. Okay, they are trying to be very precise here, okay, because there is a major theoretic thing going on here which we may not have to go, but what we have to say is that this happens because this is probability 1. So indeed xt is y minus xt by norm of y minus xt. So if I take a gradient here, then this is indeed 1. So this is what this corollary is trying to say here. Okay, so this is the main observation of the WGAN GP paper. What they say is that the WGAN, which reduces to this via Kr duality, and this duality is the existence of f star is there. Okay, that comes from the theory, let's say. Okay, so that's the existence proof is there. But then if it happens that it's differentiable, then for xt of this form, okay, which is between x and y, then the gradient of the norm of the gradient of f star must be 1. So this gives the idea for them to change the, I mean I have the proof of this, but if I do the proof or not, but at least what I can say is that already is what could be the change in the WGAN with GP. Okay, so in WGAN with GP, the change that you can do is the following, although the notations change a little bit, but it's fine, we can manage. So the change that is proposed in the notation of the original paper is x tilde pg dx tilde minus expectation of x pr and dx plus lambda expectation of x hat p x hat, and then norm of gradient of x hat dx hat minus norm and then minus 1 and then there is a square here as well, square. Okay, so with this proposition, what they have done is that they have added some additional terms. So if you see here, this is the original WGAN. Okay, where you can change x to g theta z. Okay, so this is indeed the original GAN, just that the notation changed a little bit. And what they have added is this. This is called gradient penalty. Okay, and why they did that? If you look at the term gradient penalty, they are enforcing the gradient to be 1. Okay, so they have this gradient, norm of the gradient minus 1, right? So with the lambda here, so sometimes in optimization method, sometimes you can solve constraint problem by adding a penalty. Okay, so I could have written this. So our original objective was, let us say, max of expectation of f of x minus expectation of y minus f of x, something like that. Okay, so we were doing this over f l less than equal to 1, and then this paper says that there will be an optimal f star. Now, I mean, if there is an optimal f star, and assuming that it's differentiable, then the gradient, I know that it's 1. So since I know that the gradient will be 1, why not enforce this constraint so that the optimizer will be forced to go towards f star? Okay, so whatever f I'm looking for, why not also demand further that grad of f, because I know that from this proposition that optimal has to be has to have gradient 1. Okay, so hence the original WGAN becomes like this. Okay, the original is everything same, but then I'm saying with this additional insight that then optimal 1 will come with gradient 1. So let us put this in the optimizer so that the search space narrows, because when you're solving an optimization problem, you have many ways to get lost, right? So more information you can give to the optimizer towards an optimal solution, better it is, right? It will converge faster or more stable. Okay, so this is what they did, right? But sometimes when you have constraints like this in optimization problem, then you can add the constraint with here. Okay, so in general, let me now do the in general thing. Let us say, so mean of f naught x subject to hx equals to c. This is my optimization problem. Then one way is to use duality, which is a more standard way to do things with equality and inequality constraint. But then you may want to, let's say, solve it with the primal itself, primal meaning in x itself. Then you can do something like this, but the problem is it brings in some additional, you have to bring some penalty term, okay, which in that case is lambda, and I will explain why is that. Okay, so this I can absorb this here. So this will be f naught x plus hx minus c. Now my goal is to force this in equality, right? And optimizer is about the min, so there it's about the max. So okay, I will come back to that. Okay, so but they are related. The point I want to make is how will you choose this lambda? Okay, and we have to put this lambda. Now since it's a min problem, I can take lambda very big. If I take lambda very big, then the optimizer, when it's optimizing over x, it will try to kind of make this 0. Okay, because lambda, if it's very big, then optimizer is like an agent, right? It's trying to minimize. So if it knows that it will look at both the term, and obviously it's trying to minimize the whole cost, right? So if lambda is high, let us say relative to this, or okay, so this lambda is itself a hyperparameter now. Okay, you have to look into the problem at hand. But if lambda is reasonably high, it will enforce hx to be close to c, so that this constraint you got, and additionally you want f naught x to be also getting minimized. Okay, so this is a penalty form. Okay, and where lambda is the penalization constant. Okay, so this is penalty term. This is why there we call gradient penalty, because the where its constraint is on the gradient penalty. Okay, so here, as I said, there is no fixed lambda that anyone will give you. You have to decide. Okay, depending on the experiments, you have to decide what could be a good lambda to choose. So this is a minimization problem where lambda, if it's too high, then there may be a problem that it will just make this equal and give less importance to this. So you cannot say that I will put lambda to be very, very high because I want the constraint to be satisfied. The optimizer will see a benefit of making this 0 because lambda is high, the overall cost is high, so it will just go there and make sure that this is 0. But then it might ignore this completely. Okay, so there is a balance that is needed. So there in the WGAN gradient penalty, we wanted from the theory we knew that an optimal f star will be certainly of the form that norm of the gradient is 1. So they put it as a constraint, and then as a next step they made it into a penalty form. So they made it look like this, and you can think of this as one big f naught x. F naught tilde, let us say, is the new function f naught tilde x, which is combination of this. So you do the usual unconstrained optimization on this, which unconstrained optimization we know gradient, descent, ascent, RMS prop, all are unconstrained optimization problem solvers, right? So that's the idea behind gradient penalty. Okay, so that's the most. Yeah, it's fine, right? Today still 15 minutes, right? So I do have the proof of this, why the gradient of f star will be 1. The proof will take exactly 15 minutes. Let us do this proof because there is nothing extra I have to be done. So if I do this proof, at least you will appreciate like how people think about these things, right? So okay, so let us do this. I mean, there are few things in the proof it will be left out. Okay, so there will be uses of compact space, metric space that I have not told you, but you may try to fill this as an additional thing if you want. Okay, that's not necessary, I would say, because I have not taught anything for topology in this course, but it's fine. It's just if you are interested, you go ahead and look at these things. Okay, so let us do the proof of this, of the WGAN GP paper. They had only one theorem. Okay, and so since X is a compact space, okay, so this itself is like something you need to check. Okay, this will be referred. So since X is compact, I mean, if we are in a real, then a very simple definition would be closed and bounded. Okay, so any set which is like this, okay, or any like AB, or even a Cartesian product of these, right? So usually we work on Rn, right? We don't work on very generic spaces. So for all our practical purpose, we can think of X as some closed interval, okay, and that will be compact space. So since X is a compact space, by the Villani's, Cedric Villani, right? The book that I wrote you, the Villani's book, the optimal transport book. Okay. So from there, the existence of F star for the Kantorovich max over ellipsis functions is guaranteed. Okay. So that's an existence proof, and that comes from theorem 510 part 3. Okay, so from part 3 there exists an optimal f star. So basically there is a solution to that duality form. And also by the same theorem 510, by part 2 we know that so these are the things we have to refer, okay, because we can't go too much into these things, okay. So we know that pi is an optimal coupling, so in that case, like, okay, so pi x y pi, and if we have an f star, then it's one ellipsis, so obviously probably that f star y minus f star being equal to norm y minus x is 1. So all these things are guaranteed. As I said, if we have to go deeper into these things like the WGAN, then we have to generalize things, okay. Then we have to go to optimal transport. There will be one full course on optimal transport where Villani's book will be covered, and then all these existence results, all this comes from there. So in this course obviously we cannot, because we are interested in other generative modeling as well, right. So this f star is guaranteed, and this will be one ellipsis. So there will be let us say there is an x and y for which this holds. So let x y be such that f star y minus f star x is norm of y minus x. X equals to y will be very simplistic. So we will say, let's say in general x not equal to y. So assume very trivial case, right. So assume x not equal to y, and let us construct phi t, or in fact psi t, which is norm of xt minus x. Okay, the first was actually phi t, but the next line was, so let phi t be f star xt minus f star x. Okay, I am myself, so it was phi or psi. Okay, I made a mistake already. So everywhere it's psi, and then there is no phi anywhere. So let psi t is this like shorthand, right. So psi t be f star xt minus x, and then so this t, if I'm not wrong, we already defined this, I guess. Yeah, this t was in the theorem itself. This t xt was already defined in the main theorem, okay. Xt is tx plus 1 minus ty, okay. So that's the t we are talking about. Okay, so let us continue with the proof. So psi t is f star xt and minus f star x, and then the first claim that we have is that psi t is xt minus x, which is t y minus x. So that's the first thing we want to prove, that psi t is t times norm of y minus x, okay. So let t prime be in the closed 0 1, then mod of psi t minus psi t prime is f star xt minus f star xt prime, and this is less than equal to xt minus xt prime, and this is because f star is one ellipsis, and this is equal to mod t minus t prime norm of x minus y. So let us look into this, what we did. So let us take t prime in 0 1, and let us look at the difference psi t minus psi t prime. So psi t as it's defined is f star xt minus f star x, and then we are subtracting psi t prime. So psi t prime is f star xt prime minus f star x, Sorry. Yeah, that's fine because it's dependent on t, right? So it will be t prime here, and this will remain x. So that's why this f star x will get cancelled in this difference. Okay, and only f star xt and f star xt prime will remain. And then we use the fact that f star is one ellipsis. So hence this will be less than equal to xt minus xt prime. That's the definition of ellipsis continuity. And then if we put in the values of xt and xt prime, so which was, so xt was, I hope I'm not wrong. So xt was tx plus 1 minus ty, tx plus 1 minus ty, and obviously xt prime will be t prime, right? T prime x plus 1 minus t prime y. So if you do this subtraction, then you can show that this is mod of t minus t prime, norm of x minus y. Okay, and so this essentially proves that psi function is one ellipsis, because we started with psi t minus psi t prime, and then we ended up with x minus, oh sorry, the t minus y in this case, okay? And x minus y becomes your ellipsis constant here. Okay, so this psi is one ellipsis. Okay, so psi is, this implies that psi is norm x minus y ellipsis. Okay, so a norm x minus y is the ellipsis constant we have. Now this implies psi of 1 minus psi 0. This is psi 1. I can add or subtract psi t. Okay, so I'm doing that. Psi t minus plus psi t minus psi 0. Now this is less than equal to, so I have shown that psi t minus psi t prime is less than equal to t minus t prime x minus y. So I'm going to use that in the first term. Okay, so in the first term I'm going to use that psi was one ellipsis. So this will be, I guess, 1 minus t, right? So 1 minus t norm x minus y. So this is less than equal to 1 minus t norm x minus y plus psi t minus psi 0. And well, I could have done this directly for the second part also, right? Why I'm supposed to do this here as well. So this will be t norm x minus y. Same argument, okay? So psi is one ellipsis, so this will be t minus 0 norm x minus y, and the first term was psi 1 minus psi xt will be 1 minus t norm x minus y. So all this is correct. And then if we look into this, then norm of x minus y gets cancelled. Okay? No, I mean the t norm x minus y gets cancelled, and what we are left with is just norm x minus y. So this is equal to norm x minus y. Okay. However, what we have is psi 1 minus psi 0 is, by definition, it's f star x1 minus f star x, and this is f star x minus f star y, and this is, I can reverse this, so f star y minus f star x, and this is equal to norm y minus x. So this comes directly from the definitions that we have of psi 1. Psi 1 will be f star x1 minus f star x. That's fine. Now f star x1, so x1 will be 1, so this goes away, right? So this will be x1 will be x. So then I have f star x. So this guy is f star x, and f star x or y, x0, right? Okay, yeah, it should be, the second one should be 0, right? Because that's t0, right? Not just x, right? It's 0, right? Because psi 0 is, what is going on here? Psi 1 is f star x1 minus f star x. Oh, no. I think we have to do this. There is something going on here. So psi 1 I will explicitly compute, okay, because I'm not very sure. So psi 1 is f star x1 minus f star x, and psi 0 is f star x0 minus f star x. So if I take a difference, then I have f star x1 minus f star x0. Okay, now I see. So this 0 is there, right? Now we have to look into x1. So x1 is just x, and x0 is y. So that's why we have f star x minus f star y here. x1 is x, and x0 is y. And I just flipped it. It's a mod, so I can just flip. So I made it fy minus f star, and is equal to, because because it's satisfied, okay, because f star y minus f star x must be equal to norm x minus y, right? That's the existence proof that comes from the Villani's book, right? That there are that this is possible, okay, equality is possible. So that's what we used in the last step, where we said equal to norm x minus y. Okay, so this is given, right? So this, let us say this is star, then this is from the star. Okay, the existence proof. Okay, so this is where we are now. Now if you see the, if you compare the first one, psi 1 minus psi 0, and the second one, right? And so what do we see from there, right? Psi 1 minus psi 0 itself is norm of x minus y, or y minus x, whatever you can think of. That's what we just proved, right? So what we proved just now is that this is in fact equal to, okay, this will be a little bit bad in the notes. So let us say we do it A, and this is, we call it B. So from A and B, we must have, we can also call this a C, right? So from A and B, we must have equality in C, right? Because psi 1 minus psi 0 is also norm x minus y. So this cannot be an inequality. This must be equality. Okay. So we must have equality in C. So if we have an equality, right, then what happens? So we must have an equality. So essentially psi 1 minus psi 0 must be equal to this. Okay. So this implies psi 1 minus psi 0 must be equal to 1 minus t norm x minus y plus t norm x minus y. And so that's coming from C, right? So that's due to the C, picked from C, right? And then but then if we yeah, and this itself is norm x minus y, right? Because psi 1 minus psi 0 is norm x minus y, and this is coming from B. So we can look at the last equality and maybe solve for that, right? Okay. So psi t minus psi 0. So our claim was to prove this. Okay, we are still here. Okay, so this is our claim. So we are trying to figure out, do we have this already, or it must come from there itself. So psi t, but I don't see the psi t. I have to keep psi t somewhere, right? Oh, that's the point of keeping. Let's see. So yeah, I mean one second. So there is one step that we could have waited for was like this. I wrote this in my notes, but then I thought, what was the goal of that? But now it seems like this, that I keep this psi t minus psi 0. So that's an inequality, but then these two inequality are forced to be equality. So if that is the case, then psi 1 minus psi 0, actually this one must be equal to this. And if that happens, then and psi 0, yeah, that's a good question. Like psi 0, psi t minus psi 0 is t norm x minus y, but psi 0 is 0, right? Because psi 0 is x0. X0 will be y, right? Okay, let me continue. So what I have is this. This is equal to this. Okay, so let me do that. So let me like use that fact. So C and D also, let us say this is D. So basically we are looking at this and this, so they must be equal. Then what do we have? So from A and D, okay, so from A and D, what we have is 1 minus t norm x minus y plus psi t minus psi 0. This is equal to norm of x minus y. Now this implies psi t minus psi 0 is t norm x minus y. So we are until here. Now psi 0 must be 0, right? So we have psi 0 is, so in my note psi 0 is f star x minus f star x, which because if I have psi 0, then t is 0, but t 0 gives me y. T 0 gives me y, not x. And here we do prove that, right? T minus 1 x minus y.
Yes.
So that is verified, let's say.
No, here is only t only. Minus phi 0 is norm x.
Oh, okay. But then phi 0, yeah. So eventually psi t is t minus 1, right? Okay. Okay then. So how much I have? 6, yeah, I mean, there is not much actually. So let us do this maybe another 5 minutes maybe, but with a little adjustment that we have. Okay, so this is our claim, the corrected claim, and so let V be y minus xt by norm of y minus xt, and this will be y minus 1 minus t x minus dy divided by norm of y minus 1 minus tx minus dy, right? So we have just substituted the xt. Xt we have changed a little bit, okay? It was tx plus 1 minus dy. Is this the same thing? Or xt was tx plus 1 minus dy. So can I write like this, right? So this is x minus tx. So I have to do a negative of that, right? Now let us see the xt. I mean, this itself is correct or not? I have a minus. Yeah, okay, let us do it the way we have. I think there are mistakes, so I will just do the usual xt. So this is tx plus 1 minus ty, and this is tx plus 1 minus ty. Right? Then what comes out should be what, right? Y minus x or something. So let us solve for this. So y minus tx minus y plus ty. So t of y minus x we can see here. Similarly here is the same thing. So this is So this is t of y minus x, and this is norm, and this is norm of t of y minus x. Okay, there is a lot of, yeah. So tt gets cancelled, and eventually I made a mistake maybe in the notes, but yeah, it's fine. So y minus x divided by norm of x minus y, or y minus x, so that's fine. That's our v. Now we know that, so what do we know? We know that f star xt minus f star x is psi t, and which is, okay, with our correction is t minus 1 and norm x minus y. Okay, so from here we can solve for f star xt, which is f star x plus t norm x minus y. So, and I mean t minus 1, right? T minus 1 norm x minus y. Then we take a partial derivative with or directional derivative of f star xt along the direction v. So taking directional derivative along the direction v. So we have del by del v f star xt. This is limit h tends to 0 f star x plus hv minus f star xt divided by h. Okay, so we are trying to see what is the directional derivative of f, because this will give me grad f star dot v. Okay, that's how it will be defined. So we will do some little bit of arrangements here. So h0, then f star, and I must use t here, is at xt, and then limit h tends to 0 f star xt. Xt I just expand. Basically, that's the first step. So xt, if I expand, then this is x plus t y minus x. Okay, this is okay. Tx plus 1 minus ty. Is this correct or not? Again, so this is okay. So this is xt was tx plus 1 minus ty, and I want to write it as, instead of y minus x, I could have written x minus y, right? So this is x minus y and y. So y, just y comes out, and then minus or plus t x minus y. So this is the correct way to write. I can keep x minus y or y minus x, it doesn't matter. Eventually they should get cancelled, okay? So let us write it as y plus t. So there is a lot of mistakes going on. And then plus, in the h I will do x minus y and divided by norm of x minus y. So this, I want to substitute somehow v, but v is y minus x, right? So I have to have, so what we have is hv, right? So for hv I keep x minus y. Okay, that's fine. Y minus x. So hv I will keep y minus x. So basically I replaced v by y minus x. V is eventually what did we write v? Oh yeah, v is y minus x. It's exactly there, right? This was v, right? So this is what I have substituted here. And finally what we have is minus f star xt, and whole thing divided by h, and this guy was our v. We have to prove that this is 1. Okay, That's what we are supposed to prove. There exists an f star with gradient 1, right? And that's why we impose the gradient penalty, right? So our proof will be complete if we say that this is 1. So this is equal to limit h tends to 0 f star. Now how can we write this, right? So there are t. So can I write this as some x sub t plus something, right? So that's the point. So in the notes I have written that it's x sub t plus h by norm x minus y. But obviously in our case it's not the same because there are changes. So in our case it will be perhaps 1 minus t. Okay. So the question is, how do you see this as some xt? Okay. So let us try to figure out for which t this is that, right? So xt is here, right? So I'm trying to figure out, let's say h by, so for t I have this, right? So and I'm supposed to get the h as well, h, and then y minus x is also there. It seems like I have to take y minus x common, and then I will see everything else as a t. Okay. So if I look into this, so this is y plus t x minus y plus h y minus x by norm of y minus x. So I will take x minus y common, let's say. So if I take x minus y common, then I have x minus y is something I need, right? And then everything else that is there will be taken as a t. So so x minus y, let us say I take common, and remaining thing is t minus h by norm y minus x. So the t I am looking for is this. Okay. So then I can write this. So this we can put it in a box. Then we can follow the limit. The limit h tends to 0, f star of x sub with t to be this. So x sub with t minus h by norm y minus x. So this is our f star, and then minus f star xt divided by h. So okay, this we have kind of like basically we have to evaluate the limit, and to evaluate the limit, f star xt is this, right? So we are supposed to use that. So f star xt will be this. So let us use that. Okay. So f star xt is fx plus 1 t minus 1. So this is limit h tends to 0. F star xt will be f star x as it is, and the t will be coming up later. In our case, t is t minus h by norm y minus x. That's our t, and this is like minus 1 again in our corrected form. And then we have norm of x minus y, and then minus f star xt. This term is as it is, like there. So this is minus f star x minus of t minus 1 a norm of x minus y, and whole thing divided by h. So f star x goes away, and t x minus y, norm x minus y, and minus t norm x minus y goes away. Minus norm x minus y plus norm x minus y also goes away, and only thing I see is, even if it is not true, I'll say 1. Let's go. So okay, yeah. So yeah, there are some calculations, and then we have, yeah, it's clear. Okay, so we verified this, and okay, that's it. So what we said is there are few steps, minor steps left. So we have shown the directional derivative, Okay, and then we will use this directional derivative to go up to the gradient. Okay, that's the final goal. But we can do this. It's a small step. Okay, the hard part is done. Okay. Okay then. So if you want to leave, we can leave. Okay.